Today's lecture is on sorting algorithms. Now, sorting algorithms are very useful because they allow us to, one, do binary search like we saw earlier, but then also allow us to do really any number of things, like other searches that exist. It can allow us to take advantage of certain kinds of data structures like binary search trees and AVL trees. Sorting really can allow for a lot of stuff, and it's just kind of a necessary algorithm. Now, some of you will probably bring up, either because you've been talking with the competitive programmers or anything like that, some of you will bring up that Java does have easy-to-access sorting algorithms, or perhaps you remember from last year with Python, where, yeah, there were easy-to-access sorting algorithms instead of having to write your own, and that is true. But in this class, we are learning to write our own. In particular, we'll learn to write two of them, selection and insertion, and then we're going to learn how to trace a third one called a merge sort, which I think we'll give it a little bit of an overview today and see deeper later. So for selection and insertion, we can say that there are some major pieces of each of them. For instance, in the selection sort, there are two main parts. One where we find the minimum value, and then we swap with the next unsorted element. For instance, in the very first run through a selection sort, you will find an unsorted array. It'll have one index pointing at the first element, and then one index pointing at the smallest number in the series. And then it will swap them around, so the smallest number is at the beginning, as you would probably expect. Meanwhile, the insertion sort, I would say it's a bit more complicated, but at the same time, you might have an easier time with it, you might have a harder time with it. There's really no telling. Insertion, I think, is a little harder. What it does, it has three pieces. First, it looks at the next unsorted element, the next thing we haven't put at the beginning. And then it looks back through the sorted elements and finds the proper place to place it. And then next it'll just shift everything else down. And that kind of that would kind of be a good overview of what those two things are. Let's go ahead and look at what they are in code, and hopefully some of the visuals I put with it will help you. So let's jump into that.
This is how it works. Selection is a find minimum algorithm inside of a swap, with a swap. So what it does first is it says, okay, I'm going to start at the very beginning, where j equals 0. I'm going to go through the whole array, almost, because I'm going to check the next one. J is going to keep going up because it's the outermost. It starts at 0. So we started at 0, so main index equals 0. Then I start with k, going to the next one. So it's j equals 1, so k equals 1, so long as k is less than the length of the list. If the element at k is less than my current min index, which is 0, min index changes to k. And then I get k equals 2. If elements at 2 is less than elements at min index, whatever that might be, 0 or 1, change min index to 2. Then k equals 3. I'm going to go ahead and see if the element at k is less than the one at the min index. It'll keep doing this until it gets to the end of the list. So now it's checked from 0 all the way to the end, looking for the minimum index. By this point, it's checked, and every single time it found something smaller than the last minimum, which is going to be the first element from the first time, it changes min index. So then, by this point, exactly. If I'm thinking about this in an FRQ kind of way, I've gotten my minimum. Now I got to swap them. So I use these three lines here. Why do I use these three lines? Take a good look at it and think about how this works. So with that, I have now swapped j, which is 0 on our first run through, and the minimum index. So that way now, my leftmost element is a sorted array, technically, of one element in size. The smallest. Then I come to the top. J equals 1 now. Min index is equal to 1, because now we're done with that first element. We're done with that. Now we're going to go from 1. Now k becomes 2. K is less than our thing, so we check. Is elements at 2 less than elements at 1? If it is, change the min index to 2. Keep going until we've gone through the whole length of it. We now have the min index for the next element. Swap them. So now we have a sorted array of size 2, and all the rest are unsorted. So then j becomes 2, so that's the next index. K becomes the one after it. Does that make sense? And we keep going until we've sorted everything. We keep finding the minimum value, selecting it, and swapping it out with the old one. The selection sorts get a little tougher. Now, insertion sort is the slightly more, typically it's slightly more efficient. Here's how that one goes. It's a little tougher to get. J starts at 1 because it's going to go backwards. We assume that the first element is a sorted list. Because if I have the number 5, is that sorted? Yeah, it's sorted. There are no bigger elements to the left and no smaller elements to the right. It's just a 5. Technically, that's sorted. So we skip that first element. We go through the whole list, and as we go through this pass, we get the element we're currently at, the very next element, and we say, okay, its new possible index is going to shift. Right now, both elements of j and the new possible index are in the same place. Now, keep going so long as possible index is greater than 0, and that element that we're currently at is less than the elements at my new possible index. We're checking the one before it. So if the one at 1 is smaller than the one at 0, it's going to enter the while loop, change that one, the one before it, subtract 1 from possible index. Temp still holds the old value, but now we've moved this one up, or moved it back. What happens is, I'll go ahead and draw it. It's going to be at 4, 2, 5. J equals 1, so J is pointing right here, yeah? Temp equals 2, right? Or equals the array at J, right? This one. Yeah, J is the index, and then T equals, the value. Elements at J, which is 2. Possible index is going to equal J, which is 1. So J equals 1. Possible index equals 1. J equals 1. Is possible index greater than 0? Yeah. And temp is less than the one before it, possible index minus 1, which would be 0, so it's this one. Is temp less than that one? Yes. So then in that case, elements at the possible index, which is here, equals the one before it. So 2 becomes 4. And we subtract 1 from possible index. We go up. Possible index is no longer greater than 0. So the elements at possible index, which is 0, now equals temp, which equals 2. Changing this 4 into a 2. We have now sorted the first two numbers in our array. 2, 4. And then the next one can be 5. A little weirder. Honestly, this one is one of the ones that took me a long time to actually kind of get. Yes, divide and conquer. We're going to go past my silliness there. So, here's what happens. We aren't really going to look at the code too much. Instead, we're just going to go ahead and count it out. For an array with 8 elements, what it does is it first splits them up into 2 segments, and then splits those up into 2 segments. And then if it can split those up into 2 segments, it does, which you can see there. Now they're all single elements, right? So far, that's all I've done. And then it's going to go ahead and merge them back together. So it merges these two back together. Now, are these out of order? Yes. So that means we swap them, because the merge is what handles the swap. The swapping only happens with the merge, and it will swap any of them that are supposed to swap, and make 4 sorted lists. You notice this last one doesn't swap because it doesn't have to. Does that make sense so far? Next, it'll merge these two together. It'll go ahead and sort those, probably with insertion sort. Does an insertion sort on these two. These two, these two, these two. Does a sort on these 4 and these 4. And does a sort on the full 8. We can count it up in that we only have 1, 2, 3 merges, 4. 2 to the third.
2 to the third, of course, being 8. 8 elements. Now that's 3 merges, which is going to run in logarithmic time. So we say that it is of efficiency log n. But hold on there. There's also the fact that we did have to go through the whole array at least once. So we would say it's n times log n, meaning that the efficiency of merge sort is n log n, where n is the number of elements. Better than the square of n, because obviously log n is smaller than n, and therefore it multiplied with n is going to be smaller than n multiplied with n. So that is why we might use a merge sort. It is more efficient than one of the other sorts would be. Now, there are more efficient ones out there, but they're a lot more complicated. This is about as high as we're going to go in terms of sorting. If you can get this, and we'll go through it a bit more, but if you can get these 3 sorts by the end of the year, you'll be A-okay. Alright, that's it. See ya.